Hey, long time no see. It's been quite some time since I made a proper video on this channel, so I guess we have to change that. Today's topic is going to be fairly different from what I used to do here though. So, I don't know if you ever noticed my profile pic. I'm using it not just here on YouTube, but also on Discord and in other places. Here it is in full resolution. What is it? Some of you probably know already. It's a simulation of a black hole. Specifically, a simulation of how a black hole distorts the Milky Way that is in the background. Here you can see the background image without any distortions. I rendered this image some years ago with a program I created myself. The general principle is fairly simple. Every pixel gets assigned a light ray, and the paths of those light rays are then computed step by step until the ray hits something or gets out of range. In fact, it's the same general principle as the one behind my panorama simulator, only in that program the factor bending the rays is the atmosphere, and here is the black hole's gravitational field. In that program, if the ray hits something, it was terrain, and here it is the event horizon. And in that program the space was Euclidean, while here it is non-Euclidean and not just space, but space-time. But apart from those minor details, it's almost the same. Before I tell you more about what we can see here, I'll mention one more thing. As I already mentioned, I created the program I used to generate this avatar fairly long ago, and it had some limitations. For example, it was impractical to use it to generate images in resolutions higher than 512 by 512. And that's exactly what my avatar's resolution is. But recently I got inspired to write a better version of the program with more interesting features. And this is how this new program renders the same thing in full HD resolution. Okay, now let's talk about what we can see in the image. There are two main features that stand out here, I think. First, the black circle in the middle, and second, the bright ring around it. If you know anything at all about black holes, you probably guessed what the black circle was, and you probably also guessed wrong. It is not the event horizon, or at least not exactly. For those of you that don't know, the event horizon is the boundary of a region of spacetime from which nothing can escape, not even light. In fact, the name black hole actually refers to the region of spacetime within the horizon. No light can come from there, so it would be black. So why isn't the black circle the event horizon exactly? Well, it's because it's actually bigger. What we see as black is not just the horizon, but also a region where the light coming from distant objects gets bent enough to fall into the black hole, and doesn't reach the observer. Because this way the black hole effectively blocks light from some directions, this is usually called the shadow of the black hole. Here is an image from Veritasium's video that illustrates this point. As you can see, the area from which light cannot reach the observer is quite significantly bigger than the size of the black hole itself. Let's now look at this from the other side. Let's start at the observer and trace lines of sight at different angles from the direction to the black hole. If the angle is large, the effect of the black hole is small and the rays are almost straight, so there is almost no distortion. As we get closer and closer to the black hole, the lines are bending stronger and stronger, distorting the image more and more. And at some specific angle, the lines of sight become parallel behind the black hole. So if there is some object far behind, all lines of sight at this angle from the black hole will hit it. That object will be visible on all sides of the black hole at the same angle, so as a ring. This is the bright ring we see in the simulation, called the Einstein ring. It's the image of something behind the black hole smeared by the black hole's gravity. But let's not stop there. As we get even closer, the lines of sight get bent even stronger, and lines passing above the black hole start hitting objects below it, and vice versa. Which means that inside the ring we see a copy of the image outside the ring. For example, this right here is the copy of this. Then, when we reach really close to the black hole, it is possible for the lines of sight to bend by 180 degrees, which means that in this direction we see ourselves, or what is behind us. And since this again is symmetrical around the black hole, we should expect another ring. And we have one. This is what this thin band here is. Then, even closer, at some point the light will do 360 degrees. At this point, the lines of sight will again start hitting the object directly behind the black hole, which means we will get yet another Einstein ring. This one will be much thinner, too thin to see in this simulation, but it is there. And then another one for 540 degrees, and another for 720 degrees. In fact, as far as I know, it is possible for light to circle the black hole arbitrarily many times before going away from it again, as long as it hits exactly the right spot. So we should get an infinite amount of progressively smaller rings. This is not something I can simulate though, those rings would be far too thin. Alright, you should now have a fairly good grasp of what you see here in this image. But so far, everything we talked about applied to a non-rotating black hole, known as a Schwarzschild black hole. What happens if the black hole rotates? Rotating black holes are also called Kerr black holes, after the physicist who first solved the Einstein's equations to find the metric describing them. There are a lot of similarities between rotating and non-rotating black holes, but there are also important differences. Now, how fast a black hole is spinning can be measured by the ratio of its angular momentum to its mass, usually denoted by A. If we divide that by mass again to get A over m, that number in the right units can take values between 0 and 1. 0 corresponds to a Schwarzschild non-rotating black hole. 1 is known as the extremal Kerr black hole. Extremal because a larger value of angular momentum would result in the black hole having no event horizon, but still having a singularity, which is called a naked singularity and is widely believed to be impossible in nature. Let's take our black hole and spin it up a bit. Here's what happens when we change the A over m ratio from 0 to 0.2. The black hole still looks round, but it kind of shifted to the right? There are two reasons for this, but both boil down to the same underlying phenomenon, which is called frame dragging. To put this in simplest terms, a rotating mass drags spacetime around it, so to speak. And in a sense, being at rest relative to the black hole means circling it already from an external perspective. Honestly, it's a topic for a whole separate video, but what we need to know here is that it makes orbiting the black hole in the direction of its rotation easier than in the opposite way, which means light on one side of the black hole can pass closer to it without falling in, so the shadow will be shifted a bit to one side. That's the first reason. The second reason is that the observer here is at rest relative to the black hole in some sense, but it is equivalent to moving relative to distant stars. Because of that, the whole field of view undergoes a bit of relativistic aberration. I will talk a bit more about it later. Let's continue spinning the black hole up for now. Going from 0.2 to 0.4 again shifts the image a bit, but if you look closely, you can also notice a change here on the left. This bright spot wasn't here in the previous simulation. Again, it's due to the fact that light on this side moves with the rotation, so it's not pulled in as strongly as light on the other side, in a way. Spin up to 0.6. If you squint, you can see the shadow becoming a bit flattened in the horizontal direction. And here the distinction between the shadow and the event horizon is quite important, because if we could see the event horizon, it would actually be doing the opposite. It would become flattened in the vertical direction. Okay, A over m is 0.8 now. The image is shifted to the right even more, and the left side of the shadow is changing more and more. And one more step. So far we were going in steps of 0.2, but now instead of going all the way to 1.0, we will stop at 0.999. And such a spin is easily noticeable at the first glance. The left side of the shadow is now very different from the right side. It's clear that something is going on here. And fun fact, the event horizon, which again we can't see directly, now has such a weird shape that I actually wouldn't be able to show it to you if I tried. It's a shape that cannot be embedded without distortions in a Euclidean 3D space. That's how weirdly curved it is. We've got the spin effects covered, now I want to talk a bit more about aberration. To show you how it works, I'll start adding speed towards the black hole to the observer. Remember, in all those simulations the observer is at the same spot, with the same field of view. It's only the speed that changes. You'll see why I'm stressing that in a moment. So, without further ado, let's speed up to 0.2c. Okay, what happened here? It looks as if we switched to a wider field of view, but as I stressed before, this is not the case. The reason for the change is that now that we're moving forward at a significant fraction of the speed of light, we perceive the directions of incoming light rays differently. For example, a ray coming from our side according to an external observer will look to us as if it's coming slightly from the front. Like, imagine that this is the observer's rocket. And now if the observer is moving this way and there is a light ray coming from the top, it looks like this if we look from an external perspective, right? But if we looked from the perspective of the observer, it would look like this. So the light ray is coming at an angle from the front. And if you think about it, this is not that different to what happens with other objects. Like, for example, when you are driving through rain, it seems as if the rain is falling almost horizontally and hitting the windshield directly from the front. When to someone standing on the side of the road, it is very clearly falling vertically. It's just a simple relativity of motion. The difference with light is that for the rain, the speed of rain droplets relative to the car is different than their speed relative to the ground. But for light, the speed is always c. It's only the direction that changes. This phenomenon is known as, I've said it a few times before, aberration. And it's something that was actually observed first in the 17th century by astronomers looking for the heliocentric parallax of stars. They found that stars do shift their positions during the year, but in a slightly different pattern than expected from parallax, which turned out to be aberration. Of course, the Earth is only moving at 0.01% of the speed of light, so the effect is very small. But the principle is the same. Here, at 20% of the speed of light, it is clearly visible. Apart from the aberration, one other effect is visible, but it may become slightly clearer if we accelerate a bit more. So let's shift gears to 40% of the speed of light. As expected, the field of view compressed even more, but one more thing starts to stand out. The ring around the black hole is now noticeably brighter. This phenomenon is related to aberration and is known as beaming. Basically, because the light coming from different angles is now compressed into smaller angles, it seems as if more light was coming from the front, causing the image to look brighter. If we looked backwards, we would notice the opposite, less light coming from there and dimmer image. This is a good moment to also mention one thing that is not present in this simulation, but should be. And I mean the Doppler effect. At such speeds, the light would be visibly blue shifted in the front and red shifted in the back. However, properly simulating the Doppler effect isn't easy, because RGB images don't contain enough data about the colors of the pixels. Some aspects of light spectrum don't affect the RGB values of pixels, but would affect the result of red shifting or blue shifting. So it's impossible to properly simulate, and approximations tend to give weird results. For this reason, I haven't implemented the Doppler effect yet, but I will try to do so in the future. Let's speed up again. At 60% of the speed of light, the aberration and beaming are very obvious. Now 80% of the speed of light. It looks as if we are using a fisheye lens now, but I remind you, the field of view hasn't changed, and the distance from the black hole is also the same as in the beginning. So let's do one more acceleration. And again, we won't go all the way to c, and this time it's just impossible, but we will go to 99.9% of the speed of light. And what happens is that the field of view gets compressed and brightened a lot. And I mean a lot. If we included the Doppler effect, most of what we see here would actually be invisible, because it would be blue shifted to somewhere around X-rays or even gamma rays. Alright, let's slow back down to 0. Now that we've discussed all this stuff, we are ready to take a look at the animation I actually wanted to talk about. If you saw my community post or stuff I posted in Discord servers, you probably have seen it already. It's a simulation of what it would look like to go approximately in a circle around a rotating black hole at 80% of the speed of light. An additional detail here is that we are not circling the black hole in its equatorial plane, so to speak. The black hole's axis of rotation is perpendicular to the galactic plane here, and our circle is inclined at 50 degrees to that plane. We can see all the effects I talked about until now in this animation. and there are also some cool effects when the black hole passes in front of the galactic plane. You can also see the distortion of the black hole's shadow changing as we look at it from different sides. Note that I was deliberately avoiding using the word orbit here, even though I have called this animation orbiting a black hole in a few places already. This is because it's not an entirely appropriate name. In this animation, the observer's motion is completely divorced from the black hole's gravitational field. I'm just setting the observer's position and speed for each frame, but those are not positions and speeds an observer would have in an actual free orbit. I will probably create a simulation with a proper orbit in the future, where the speed would be adequate for the distance from the black hole, and the observer's trajectory would be computed in accordance with the black hole's gravity, but this is not such a simulation. But make no mistake, this trajectory not being a free orbit doesn't mean that it's impossible to move like that. An observer could follow such a trajectory, only they would have to keep using engines to stay on it. This is why I keep talking about free orbits, as in orbits that don't require any effort to stay on, where the observer is in freefall. The motion here could, I guess, still be called an orbit, only it's not a free orbit. As a side note, the word circle might not be actually entirely appropriate here either, though this is much harder to tell. To be precise, the observer here remains at a constant radial coordinate r. In spherical coordinates in a flat space, this would mean moving in a circle, but geometry of the space around the black hole is much weirder than that. So, while the trajectory probably doesn't differ from a circle by much, it's most likely not, strictly speaking, a circle. And this is all I had for you today. I hope you liked the animations and the brief introduction to effects related to black holes. If you liked this video, let me know in the comments, and I'll try to make more like it. There is still much stuff that could be said about black holes and relativity in general. But for now, thank you for watching this video, and see you in the next one.